A critical challenge for autonomous driving is the domain gap between model training and deployment, and this problem is even more challenging under the multimodality scenario. This work, called DualCross, Cross-Modality, Cross-Domain Adaptation for Monocular Bird's-Eye View Perception, is trying to bring new insights into this problem. When dealing with adaptation, previous methods often assume two scenarios. One scenario is cross-domain, where training data are captured in a different domain from the testing data. For example, day and night, light and dark, city from country A and city in country B, but the input of sensor modalities are the same across the training and testing phases. The second scenario is cross-modality, where the testing data have different, often fewer, type of sensor modalities available than the training data, but they assume the same data domains. We found that a more realistic setting is the simultaneous domain gap and modality gap between the training and testing phases. We consider the camera and LiDAR modalities being available during training, and only camera is available during testing. Under this circumstance, we found that using the additional modality as direct supervision, meaning taking LiDAR as depth supervision, leads to worse results than not using it at all, as shown in the table. We hypothesize such phenomenon is caused by the additional training and testing gap from the training exclusive LiDAR modality. To account for this challenge, we propose a knowledge distillation strategy named DualCross to transfer the LiDAR knowledge from the training domain to the camera model in the testing domain. DualCross includes three components. First, a LiDAR teacher, which uses voxelized LiDAR point clouds to transform the information from image features to the bird's eye view frame. It provides essential knowledge on how to guide image learning given LiDAR information. Second, a camera student, which takes only source image as input, predict the depth distribution, project the image feature embedding into the bird's eye view space, and then perform the downstream detection and segmentation tasks with the bird's eye view feature map. The student is supervised by the source domain ground truth LiDAR point cloud as well as the teacher model. Finally, two discriminators are used to align features from source and target domains. Here, we show a day-to-night adaptation scenario where we compare DualCross with direct LiDAR supervision and adversarial learning model. We found that our model leads to more stable and consistent segmentation results. DualCross achieved best bird's eye view segmentation performance in adaptation settings compared with vanilla domain adaptation and depth supervised adaptation methods. Superior performance is also observed for segmentation tasks under various domain shifts, including day to night, dry to rain, Boston to Singapore, and nuisance dataset to lift dataset. In addition to segmentation tasks, we also observed DualCross achieving leading results on detection tasks under both modality and domain shifts, as shown by the left table. We also find that DualCross performance scales well with more powerful encoder backbones, as shown by the right table. Here, we show that all our components contribute to the final performance. Note that, as shown in the beginning, direct LiDAR supervision without knowledge distillation leads to worse results. With our proposed components, we're able to substantially improve the segmentation performance from 6 to 17 IOU. In summary, we introduce cross-domain and cross-modality scenario, an overlooked but realistic problem setting in 3D domain adaptation in the wild. We propose DualCross, a robust test-time camera-only 3D model that works in complicated and dynamic scenarios with minimum sensors available. We also achieve state-of-the-art performance on segmentation and detection tasks. Please check our project website for more details and code release. Thank you.